Hello and welcome to Late Night Physics. Before we begin, take a moment to hit that like button, subscribe if you haven't already, and let us know in the comments where you're watching or listening from. Whether it's a quiet bedroom, a cozy living room, or even somewhere under the stars, the very light around you, the soft glow, the flicker of a lamp, the shimmer of moonlight, carries secrets that scientists have been unraveling for centuries. Tonight, we're going to take a gentle journey into one of the most fascinating mysteries of the universe: how light can behave as both a wave and a particle at the same time. It's a concept that challenges intuition, stretches our imagination, and connects everything from the tiniest photon to the vast cosmos. So as you settle in and allow your mind to drift, imagine that each ray of light passing through your room carries a story of discovery, experiments, and the subtle dance between waves and particles that has baffled even the greatest minds. By the end of this journey, you'll see light not just as illumination, but as a bridge between the visible world and the strange, beautiful quantum universe that surrounds it. And as always, we'll keep the pace slow, the tone calm, and the curiosity alive, perfect for relaxing, learning, and maybe even drifting off to sleep. Light is everywhere. It fills the spaces around us, slipping through windows, reflecting off surfaces, and carrying colour, warmth, and energy to every corner of our world. And yet, for all its familiarity, light remains profoundly mysterious. At first glance, it seems simple: a straight beam from a lamp to your hand, or the soft glow of morning sunlight spreading across a room. But beneath this simplicity lies a complexity that has puzzled scientists and philosophers for centuries. Light does not behave in the way we might intuitively expect. Sometimes it spreads out like ripples on a pond, creating patterns and interference, and other times it appears as discrete packets of energy, bouncing from one particle to another. This duality, the simultaneous wave-like and particle-like nature of light, is not just a curious trick of nature. It is a window into the deeper workings of reality itself, revealing that the universe is far stranger and far more elegant than our daily experience might suggest. The concept of duality challenges the very way we think about cause and effect, presence and motion, and the relationship between observation and reality. Philosophers have long pondered these questions, but it was the meticulous experimentation and careful theorizing of scientists that began to untangle the threads. For example, in the early 19th century, George Stokes examined the polarization of light, discovering subtle changes in orientation that could only be explained if light behaved as a wave with directional properties. Around the same time, Jean-Baptiste Biot studied optical activity in crystals, observing that certain materials could rotate the plane of polarized light in ways that defied simple explanation. These insights were not merely technical details. They hinted at a deeper truth, that light carried hidden patterns and structures, patterns that demanded a new way of understanding the fundamental nature of energy and matter. Even today, the study of light continues to bridge multiple disciplines. In information theory, photons can encode data with remarkable efficiency, forming the backbone of fiber optic communications. In cosmology, light travelling across billions of light years carries the story of the universe itself, revealing the formation of galaxies, the ripples of gravitational waves, and the afterglow of the Big Bang. Light is both messenger and message, a thread connecting our observations to the underlying laws of physics. It is no exaggeration to say that to study light is to study reality, because almost every principle we take for granted — space, time, energy, motion — reveals its nuances through how light interacts with the world. And yet, despite the mathematical precision and experimental rigour, there is a certain delight in the playfulness of light. It can split into colours in a prism, create iridescent patterns on soap bubbles, or bend and twist in ways that feel almost magical. This is a universe that rewards curiosity, where careful observation leads to startling insights, and where small experiments can illuminate truths as grand as the cosmos. The curiosity-driven exploration of light has carried human thought from the simple observations of candle flames to the sophisticated quantum theories of today. Scientists such as Stokes and Biot remind us that even subtle, patient investigations can uncover profound principles that continue to inform modern optics, photonics, and quantum research. As we begin to explore light more deeply, it is worth pausing to appreciate both its immediacy and its depth. A single photon is unimaginably small, carrying energy measured in fractions of an electron volt, yet trillions of photons can illuminate a stadium or warm the surface of a planet. The wave-like patterns they produce can span meters in a laboratory interference experiment or millions of light-years in cosmic observations. Light occupies an extraordinary range of scales, and understanding it requires a willingness to embrace both simplicity and complexity at once. In this space, we can approach the study of light as both scientists and dreamers, observing, measuring, theorizing, and marveling at the astonishing choreography of waves and particles moving through the fabric of reality. It is this blend of familiarity and mystery that makes light so captivating. It reminds us that even the most ordinary elements of our world can conceal astonishing truths. The gentle bending of sunlight through a window, the subtle shimmer of a crystal, the rhythmic interference patterns in a laboratory experiment. These are all glimpses into the dual nature of light. And as we explore this duality, we will encounter experiments, theories, and discoveries that challenge our intuition, expand our understanding, and connect us to centuries of human curiosity and insight. Light is, in every sense, a story of exploration, and each ray carries with it the possibility of wonder, discovery, and profound understanding. By observing light with patience, care, and curiosity, we begin to see the universe not just as a collection of objects and forces, but as a coherent, intricate, and deeply interconnected tapestry. The wave-like spreading, the particle-like collisions, the subtle rotations and oscillations, all these behaviors are more than scientific curiosities. They are clues, signposts, and invitations to look deeper. And so, as we begin this journey into the behavior of light, we enter a world where intuition is only a starting point, where questions lead to more questions, and where the act of observation itself becomes part of the unfolding story. Light is simple enough to see, yet complex enough to fascinate for centuries, and it is in this duality, both familiar and extraordinary, that we find the gateway to understanding the fundamental structure of reality. Long before the modern theories of quantum mechanics and electromagnetic waves, the study of light was already a story of patient observation and careful experimentation. In the 17th century, scientists like Willebrord Snell were refining the laws of refraction, investigating how light bends when passing from one medium to another. Snell observed that the angle at which a beam of light enters a denser medium relates in a precise way to the angle at which it exits, a principle we now express as Snell's law. These measurements were delicate, requiring precise angles and careful alignment, and they laid the foundation for centuries of optical research. By measuring the bending of light through water, glass, and air, early scientists discovered that refraction was consistent, predictable, and mathematically describable, showing that even phenomena that appear subtle and ordinary can follow strict rules. In the early 19th century, Etienne Louis Malus examined the polarization of light, a property that reveals the orientation of light waves as they oscillate. He observed that when light reflects off certain surfaces or passes through polarizing crystals, its vibration is restricted to specific directions. This was not an obvious property. To the untrained eye, light still appears uniform and continuous. Yet Malus's experiments, performed with careful alignment of crystals and repeated observations, revealed a hidden structure in light, an internal order that hints at the wave-like nature of illumination. Polarization would later prove essential in understanding interference, optical devices, and even the transmission of information in modern communications. Meanwhile, Augustin Jean Fresnel was developing and refining the wave theory of light, challenging the then dominant particle view established by Isaac Newton. Fresnel introduced mathematical descriptions of diffraction, showing that light could bend around edges and spread into patterns rather than travelling solely in straight lines. His work explained phenomena that the particle theory struggled with, such as the formation of bright and dark fringes in interference experiments. Fresnel's predictions were confirmed with careful experiments, such as observing light passing through thin slits and around obstacles, where wave-like patterns emerged in precise and repeatable ways. These studies revealed that light is not simply a stream of particles, but exhibits properties akin to ripples on water, creating regions of constructive and destructive interference that are mathematically predictable. The work of these early scientists illustrates a crucial principle of science. Meticulous observation and quantitative measurement often reveal patterns invisible to intuition. Each experiment, whether tracking the angle of refraction, the direction of polarization, or the interference pattern from a slit depended on patience, precision, and repeatability. Instruments were simple by today's standards: crystals, prisms, slits, and protractors, but the care with which they were used allowed discoveries that remain foundational to modern optics. Laboratories in Paris, Leiden, and London became centres for rigorous inquiry, where ideas were shared, debated, and tested, gradually building a framework that would evolve into the wave-particle duality we now explore. These historical experiments also provide context for modern optics. The principles established by Snell, Malus, and Fresnel are directly connected to technologies we use today, from polarized sunglasses that reduce glare to fiber optic communications that transmit light over hundreds of kilometers with minimal loss. The understanding of diffraction informs the design of microscopes and telescopes, allowing us to observe objects far smaller or further away than could be imagined in the 18th century. Even quantum optics, with its delicate control of single photons, owes a conceptual debt to these early insights into the behavior of light. Science, in this sense, is an iterative process. Each generation builds upon the observations and measurements of those before, refining, testing, and sometimes challenging their conclusions. Light studies exemplify this iterative nature perfectly. Initial laws of refraction provided a first approximation. Polarization experiments revealed hidden complexity, and wave theory offered a more comprehensive explanation, yet still did not capture the full quantum reality discovered a century later. Through it all, the story of light teaches us that curiosity, precision, and persistence are the guiding lights of discovery, illuminating truths that are both subtle and profound. Even as we reflect on these experiments, there is room for delight and wonder. Consider a simple prism refracting sunlight into a spectrum of colours. To the casual observer, it is merely beautiful. To a scientist in the 19th century, it was a clue, a hint that light is composed of discrete components and obeys precise physical laws. The elegance of these experiments lies not just in their results, but in the careful attention and ingenuity that revealed patterns hidden in plain sight. By following this thread from refraction to polarization to diffraction, we see the cumulative power of observation and reasoning, the incremental unfolding of understanding that ultimately allows us to perceive the dual nature of light, a wave and a particle intertwined in ways that continue to challenge and inspire. In exploring these early discoveries, we also encounter a human element, the patience, creativity, and curiosity of researchers who pursued subtle phenomena without the aid of modern instruments. Their work reminds us that science is a conversation across generations, a chain linking careful measurement, mathematical insight, and relentless questioning. Each precise angle measured, each crystal rotated, each light fringe observed adds a piece to the puzzle, a mosaic that reveals not only the properties of light but also the enduring nature of inquiry itself. It is this dedication, this commitment to observing the world with care and curiosity, that allows us to appreciate light not merely as illumination, but as a gateway to understanding the principles that structure our universe. When we observe light in everyday life, it often appears to travel in straight lines, illuminating objects and bouncing predictably off surfaces. Yet, as we look more closely, we find that light is far more dynamic than this simple picture suggests. The wave nature of light reveals itself in phenomena that defy the expectation of straight paths. One of the earliest frameworks to explain this behaviour is the Huygens-Fresnel principle, developed through the work of Christian Huygens in the 17th century and refined mathematically by Augustin Jean Fresnel in the early 19th century. Huygens proposed that every point on a wavefront of light can be considered a source of secondary spherical waves, spreading outward in all directions. The combined effect of these secondary wavelets determines the overall propagation of the light wave. This insight allowed scientists to understand diffraction, the bending of light around edges and through narrow apertures, which had previously seemed mysterious. Fresnel expanded on this principle, providing detailed calculations that predicted interference patterns with remarkable accuracy. By passing light through two closely spaced slits, he showed that bright and dark fringes appear on a screen, a result of constructive and destructive interference where the peaks and troughs of light waves reinforce or cancel one another. These observations confirmed the wave nature of light in a tangible and measurable way. The patterns were precise. The spacing between fringes depends on the wavelength of light, and the separation between the slits, with visible wavelengths ranging from roughly 400 to 700 nanometers. Fresnel's work demonstrated that even phenomena occurring on scales far smaller than the width of a human hair could be described and predicted mathematically, and it set the stage for future experiments that would probe light with even greater precision. As the understanding of waves developed, the advent of quantum mechanics introduced a new perspective. Max Born, in the 1920s, proposed a probabilistic interpretation of wave functions, suggesting that the amplitude of a wave does not represent the energy of a particle directly, but the probability of finding a particle in a particular location. This approach transformed the classical picture of continuous waves into a probabilistic framework, allowing light to be treated as both wave and particle simultaneously. In this interpretation, the interference patterns observed in experiments like the double-slit experiment are no longer merely collective behaviors of many photons, but emerge even when individual photons are sent one at a time, their probabilities governed by the underlying wave function. This probabilistic view bridges the familiar wave behaviors of light with the subtler, particle-based phenomena explored in the quantum realm, revealing that even individual photons carry a wave-like signature in the probabilities of their detection. Coherence theory, which gained prominence through the work of Roy J. Glauber in the 1960s, further refines our understanding of how waves combine and interact. Coherence describes the degree to which light waves maintain a fixed phase relationship over time or space. In practical terms, it explains why lasers produce such a sharp, focused beam. The photons emitted are highly correlated, oscillating in unison across vast distances compared to ordinary light sources. Coherence is also crucial for observing interference effects in quantum optics experiments, where delicate correlations between photons reveal the underlying wave structure, even at the single particle level. Understanding coherence allows us to manipulate light in ways that enable high-precision measurements, optical communication, and the generation of non-classical states of light used in quantum computing. Diffraction, interference, and polarization are all manifestations of these wave principles. Diffraction describes the spreading of light as it passes through apertures or around obstacles, producing characteristic patterns that can be predicted mathematically. Interference arises when two or more waves overlap, creating regions of increased or decreased intensity depending on whether the peaks and troughs align or cancel. Polarization adds an additional layer, describing the orientation of the oscillating electric field in a light wave. Together, these phenomena illustrate the richness of the wave model, explaining a wide variety of observations from the rainbow patterns in thin oil films to the precise fringes measured in laboratory experiments. By connecting classical wave behavior to the probabilistic nature of quantum mechanics, we begin to see a unified picture of light that is both elegant and powerful. The Huygens-Fresnel principle explains how wavefronts propagate. Born's probabilistic interpretation provides a framework for individual photons, and coherence theory describes the relationships between multiple photons over space and time. These frameworks allow us to predict and understand experimental outcomes with astonishing accuracy, whether in the laboratory or across cosmic distances. Light can diffract around an object, interfere with itself across multiple slits, or maintain precise phase coherence over kilometers in a laser beam, and all these behaviors fit naturally within the same overarching principles. Even the smallest details are illuminating. For example, the wavelength of red light is roughly 650 nanometers, while violet light is around 400 nanometers, a difference that leads to the visible separation of colors in diffraction patterns. The spacing of interference fringes in a typical laboratory setup might be on the order of millimeters, yet these patterns emerge from interactions on scales thousands of times smaller than the width of a human hair. Such contrasts between scale highlight the astonishing precision inherent in wave phenomena and the meticulous nature of the measurements required to observe them. Through these principles, we gain not only predictive power, but also a deeper appreciation for the inherent beauty of light. Each experiment, from simple double-slit interference to the delicate control of coherence in quantum optics, reveals patterns that are both visually striking and conceptually profound. The wave perspective provides the language and tools to describe the subtle interplay of light across space and time, and when combined with quantum insights, it forms the bridge to understanding the full dual nature of light. By following these threads, we prepare to explore the behaviors of light in ways that are both intuitive and counterintuitive, where waves and particles intertwine to create the complex, fascinating, and endlessly instructive phenomena that continue to inspire scientists and observers alike. Long before the wave theory of light gained prominence, Isaac Newton proposed that light consisted of tiny particles, which he called corpuscles. In his experiments with prisms and lenses during the late 17th century, Newton observed that light could be refracted, reflected, and dispersed into a spectrum of colours. He interpreted these behaviours as the motion of small, discrete particles emitted from luminous sources. According to the corpuscular theory, light particles travelled in straight lines, bouncing off surfaces or bending when entering denser materials due to a force acting upon them. Newton's explanations were elegant in their simplicity and matched many observations of the time, yet they could not fully account for interference patterns or diffraction phenomena, which would later reveal the wave-like nature of light. Despite its limitations, Newton's particle model laid important groundwork for thinking about light as quantized energy. In the late 19th century, Wilhelm Wien extended these ideas through his studies of blackbody radiation. Wien approximated the energy carried by discrete packets of light, suggesting that the energy of these quanta is proportional to the frequency of the radiation. This concept, though initially an empirical fit for thermal spectra, anticipated the formal introduction of photons by Max Planck and Albert Einstein. Wien's work highlighted that under certain conditions, treating light as particles provides a more accurate description than purely continuous waves, especially when considering energy transfer in discrete steps. Louis de Broglie took this idea even further in 1924, proposing that not only light, but all matter exhibits wave-like properties. He suggested that particles such as electrons have associated wavelengths, determined by their momentum, bridging the gap between the particle concept and wave behaviour. De Broglie's hypothesis was initially radical, challenging the classical notion that waves and particles occupied distinct domains. Yet his theory was soon validated through electron diffraction experiments, showing that particles of matter can create interference patterns similar to light waves, demonstrating a deep symmetry in nature. This realization helped form the foundation for modern quantum mechanics, where particles and waves are two sides of the same coin. Between the classical particle model and full quantum descriptions, semi-classical approaches provide useful frameworks for understanding light's behavior. In these models, light is treated as a stream of particles that also interact with a wave-like field, allowing predictions of phenomena such as stimulated emission in lasers or the absorption of light by atoms. Semi-classical theories have been particularly valuable in developing technologies that manipulate photons, including optical amplifiers, photodetectors, and even certain aspects of fiber optic communication. They demonstrate that particle behavior is not in opposition to wave behavior but rather complementary, each providing insight into different aspects of light's multifaceted nature. Recognizing light's particle characteristics allows us to explain phenomena that wave theory alone cannot address. For instance, the photoelectric effect, where light striking a metal surface ejects electrons, is naturally interpreted in terms of photons delivering discrete amounts of energy. The energy of each photon is proportional to its frequency, a relationship formalized as E equals Planck's constant times the frequency of the photon. This quantization explains why low-frequency light, no matter how intense, fails to eject electrons, while high-frequency light does so even at low intensities. Here, particle behavior provides clarity where continuous waves fall short, illustrating the necessity of considering both perspectives when studying light. Through the historical arc from Newton to Wien to de Broglie, we see a gradual refinement of the particle concept. It is not merely an archaic idea to be replaced by waves, but a complementary framework that enhances our understanding. By acknowledging that light can behave as a particle under certain conditions, we prepare to integrate this view with wave-based models, forming the cohesive picture necessary for quantum mechanics. Particle models inform our understanding of energy transfer, photon interactions, and quantum processes, while wave models explain interference, diffraction, and coherence. Together, they reveal the extraordinary duality that lies at the heart of light. This dual perspective also reminds us that scientific models evolve, often beginning with simple explanations and becoming progressively more sophisticated as experiments uncover new layers of complexity. Newton's corpuscles described many familiar optical phenomena accurately. Wien's photon energy approximations accounted for thermal radiation spectra, and de Broglie's matter waves bridged the conceptual gap between particles and waves. Each step builds upon careful observation, precise measurement, and imaginative theoretical insight. The particle model of light is thus not a relic of the past, but a crucial part of the tapestry of understanding that allows us to see light in all its richness, complexity, and subtlety, a story that continues to unfold in laboratories and observatories around the world today. Even as we explore these concepts, there is an aesthetic delight in contemplating light as a collection of tiny, discrete quanta moving through space. Each photon, unimaginably small and fleeting, carries with it energy, momentum, and information about the world it traverses. Yet collectively, photons form waves, create interference patterns, and give rise to the colours and intensities that shape our experience of the world. This interplay of individuality and collectivity, particle and wave, is not only scientifically profound but also deeply inspiring, revealing that the nature of light is far richer than intuition alone might suggest. It invites us to approach the study of the universe with curiosity, patience, and a willingness to embrace complexity, knowing that even the simplest phenomena can conceal layers of wonder. Light, as we have begun to see, cannot be fully understood without considering its intimate connection to electricity and magnetism. In the mid-19th century, James Clerk Maxwell unified these two seemingly separate forces into a single framework, encapsulated in what we now call Maxwell's equations. These four elegant equations describe how electric charges produce electric fields, how currents and changing electric fields generate magnetic fields, and crucially, how changing magnetic fields in turn produce electric fields. One of the most profound consequences of Maxwell's work was the prediction that oscillating electric and magnetic fields can propagate through space as self-sustaining waves, moving at a speed that precisely matches the measured speed of light. In essence, Maxwell revealed that light itself is an electromagnetic wave, with the electric and magnetic components oscillating perpendicular to one another and perpendicular to the direction of propagation, a transverse wave, unlike the compression waves we might observe in water or air. Maxwell's theoretical insight might have remained an elegant abstraction, if not for the experiments of Heinrich Hertz in the late 19th century. Hertz set up oscillating circuits that produced electromagnetic waves at radio frequencies and detected them across a laboratory, confirming that Maxwell's equations describe real, propagating waves. These experiments were groundbreaking, showing that light is just one member of a vast spectrum of electromagnetic radiation, including radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. The implications were far-reaching. For the first time, scientists could see a unifying principle connecting phenomena from the invisible radio signals bouncing across continents to the bright light illuminating a room, and even the X-rays revealing bones beneath the skin. Hertz's work not only validated Maxwell, but also laid the foundation for modern telecommunications, radar, and the entire field of spectroscopy. Building on this framework, Hendrik Lorentz developed his electron theory in the early 20th century, connecting classical electromagnetism to the behavior of charged particles and setting the stage for quantum interpretations. Lorentz proposed that atoms contain electrons bound in ways that respond to electromagnetic fields, allowing light to be absorbed, emitted, and scattered in quantized interactions. His theory explained phenomena such as the refraction and dispersion of light in materials and helped describe how the electromagnetic field interacts with matter. In effect, Lorentz bridged the gap between the continuous wave description of light and the emerging particle perspective, showing that waves and particles are not separate but complementary ways of describing interactions between light and the charged constituents of matter. Even within this classical framework, Maxwell's equations predict behaviors that suggest both wave-like and particle-like interactions. The energy carried by an electromagnetic wave can be transmitted continuously over space, yet when it interacts with matter, it often does so in discrete amounts, a hint of the photon concept that would later be formalized in quantum mechanics. The magnitude of the electric and magnetic fields, the orientation of their oscillations, and the rate at which the fields change all determine how energy is delivered to atoms, whether in a laboratory, a technological device, or the vast reaches of interstellar space. This dual perspective allows us to understand why light can produce interference fringes in a double-slit experiment, and simultaneously knock electrons out of a metal surface in the photoelectric effect. Relativistic effects also subtly influence electromagnetic waves, particularly at high frequencies or over long distances. The finite speed of light means that changes in electric and magnetic fields propagate with a slight delay, referred to as retarded potentials, which must be considered when modelling radiation from moving charges or accelerating particles. At the same time, the principles of special relativity, formulated by Albert Einstein in 1905, demonstrate that observers moving relative to a light source perceive changes in frequency and wavelength. The familiar Doppler effect extended to electromagnetic waves. These considerations are essential for understanding light from rapidly moving astronomical objects, the behavior of radiation in particle accelerators, and the precision required in modern technologies such as GPS and radio astronomy. The transverse nature of a light also gives rise to phenomena such as polarization, where the direction of the electric field oscillation can be manipulated to filter or control light. Polarized sunglasses, optical filters and cameras, and even liquid crystal displays rely on controlling the orientation of these fields. In laboratory experiments, polarizers and wave plates demonstrate that light can be split, rotated, and recombined with predictable outcomes, all of which can be precisely described by the mathematics of Maxwell's equations. These manipulations, though technically sophisticated, rely on the same principles that Maxwell and Hertz elucidated over a century ago, highlighting the enduring relevance of classical electromagnetic theory. By exploring Maxwell's framework, Hertz's conformations, and Lorentz's electron theory, we gain a comprehensive picture of light as both a wave and an agent of energy transfer. We see how the oscillating fields of electromagnetic waves govern diffraction, interference, and polarization, and how interactions with matter suggest discrete particle-like exchanges. The classical and quantum perspectives are intertwined, each providing insight into different aspects of light's behavior. Whether we're examining the gentle spread of light through a prism, the precise interference fringes in a laboratory, or the radio waves traveling across continents, electromagnetic theory allows us to describe, predict, and manipulate light with remarkable accuracy. Even subtle details carry significance. Visible light spans wavelengths from roughly 400 to 700 nanometers, with energy carried in each wave proportional to its frequency. Radio waves, by contrast, can extend from a few millimeters to hundreds of kilometers in wavelength, yet they obey the same Maxwellian principles, differing only in scale. The coherence, amplitude, and phase of these waves determine their interactions with matter and their utility in technology, from everyday illumination to the most advanced communication systems. Understanding electromagnetic waves in this detailed and nuanced way prepares us to embrace the deeper quantum descriptions of light, revealing a universe in which waves and particles coexist seamlessly, each perspective illuminating aspects of reality the other cannot fully capture. Through careful study of Maxwell's equations, the experiments of Hertz, and Lorentz's theoretical insights, we begin to see light as a bridge between classical physics and quantum mechanics. Its behavior is governed by well-defined laws, yet it retains the subtlety and complexity that makes each interaction unique. The propagation of waves, the oscillation of electric and magnetic fields, the transfer of energy in quantized interactions, and the influence of relativistic effects all combine to form a picture that is both precise and awe-inspiring. Light is at once tangible and elusive, simple in concept yet profound in consequence, and understanding it requires both rigorous analysis and a willingness to appreciate its inherent elegance and subtlety. At the turn of the 20th century, a profound shift occurred in our understanding of light. Max Planck, studying the radiation emitted by heated objects, found that classical physics could not account for the observed spectra. In particular, the intensity of radiation at high frequencies diverged sharply from predictions based on continuous wave models. To resolve this, Planck introduced the idea that energy is emitted or absorbed in discrete packets, which he called quanta. Each quantum carries an amount of energy proportional to the frequency of the radiation, expressed mathematically as E equals Planck's constant times the frequency. This simple, yet revolutionary proposal explained the observed blackbody spectra and laid the foundation for what would become quantum theory. Planck's quantization suggested that light, although exhibiting wave-like properties, could also interact with matter in discrete steps. Albert Einstein extended this concept in 1905 when he addressed the photoelectric effect, a phenomenon in which light striking a metal surface ejects electrons. Classical wave theory predicted that increasing the intensity of light should increase the energy of ejected electrons, yet experiments consistently showed that only the frequency of the light mattered. Einstein proposed that light consists of individual quanta, later called photons, each carrying energy E equals Planck's constant times the frequency. If the photon energy exceeds a threshold determined by the material, it can liberate an electron. This insight resolved a long-standing experimental puzzle and provided compelling evidence that light has particle-like characteristics, in addition to its wave behavior. Philippe Lenard had conducted precise experiments on the photoelectric effect, measuring the kinetic energy of electrons ejected from various metals under different frequencies of light. His meticulous work demonstrated the threshold frequencies below which no electrons were emitted, regardless of the intensity of the light. Einstein's theory not only explained these observations, but predicted the quantitative relationship between photon frequency and electron energy, a relationship that subsequent experiments confirmed with increasing precision. These findings highlighted the necessity of a new framework for understanding light, one that combined wave properties with discrete energy interactions, and marked a decisive step toward the development of quantum mechanics. Arnold Sommerfeld, working in Germany around the same period, further refined quantum ideas by applying them to atomic structures. Sommerfeld extended Bohr's earlier model of the atom, incorporating elliptical orbits and relativistic corrections to account for fine structure in spectral lines. While his work focused on electrons and atomic spectra, it also underscored the limitations of purely classical approaches and the importance of quantized interactions. Planck, Einstein, and Sommerfeld collectively shaped the early quantum landscape, showing that light and matter operate according to principles that defy classical intuition, yet can be precisely described through quantization and probabilistic reasoning. The probabilistic nature of light emerged naturally from these developments. Experiments revealed that even when photons are emitted individually, the patterns they produce, such as in the double-slit experiment, are consistent with the probabilities dictated by their underlying wave functions. Each photon behaves unpredictably in isolation, yet the accumulation of many photons creates interference patterns characteristic of waves. This duality, randomness at the level of individual particles and order at the level of ensembles, is a cornerstone of quantum theory. It reflects a fundamental departure from classical determinism, where outcomes were assumed to be entirely predictable given initial conditions. Several anomalies also highlighted the inadequacy of classical physics. Ultraviolet catastrophe, the unexplained saturation of blackbody radiation at short wavelengths, was a key problem Planck addressed. The precise dependence of the photoelectric effect on frequency rather than intensity contradicted wave theory. Spectral lines of hydrogen and other elements, measured with high precision using diffraction gratings, displayed fine structure and splitting that could not be accounted for by classical electromagnetism alone. These anomalies demanded a conceptual revolution, one that combined Planck's quantized energy, Einstein's photons, and Sommerfeld's refined atomic models into a coherent framework. Even in the laboratory, these concepts carried practical implications. The energy of a photon in visible light ranges roughly from 2 to 3 electron volts, yet in ultraviolet light it rises to around 10 electron volts, sufficient to break chemical bonds or liberate electrons from metals. Blackbody radiation at room temperature peaks in the infrared, around 100 terahertz, while the sun emits a broad spectrum, from radio waves through visible light to ultraviolet, emphasizing the universality of Planck's quantization principle across a vast range of energies. These concrete numbers help bridge abstract theory to tangible reality, illustrating the precise ways in which photons carry energy and interact with matter. By revisiting the contributions of Planck, Einstein, Lenard, and Sommerfeld, we see the emergence of a new understanding of light, one in which waves and particles are not mutually exclusive but complementary descriptions of a deeper reality. Quantization allows us to calculate energy exchanges accurately, while probabilistic wave functions explain patterns and interference effects. The anomalies that classical theories could not resolve are not failures, but invitations to deeper insight, revealing a universe that operates according to rules both subtle and surprising. Light is, therefore, both particle and wave, discrete and continuous, simple in its daily appearance yet astonishingly complex in its fundamental behavior. These ideas set the stage for the modern quantum view of light, where photons, probability waves, and energy quanta coexist in a seamless framework. Observing these principles, from the emission of a single photon to the patterns formed by trillions of photons in an interference experiment, we begin to appreciate the elegant balance between order and randomness, simplicity and complexity that governs the behavior of the universe. It is in this interplay that the foundations of quantum optics, spectroscopy, and even modern technologies like lasers and photodetectors are rooted, showing that the revolutionary insights of Planck, Einstein, and Sommerfeld continue to illuminate our understanding of light more than a century after their discoveries. The dual nature of light challenges our most basic intuitions, suggesting that what we observe is only part of a more subtle reality. Niels Bohr articulated this insight through his principle of complementarity, proposing that light can display wave-like or particle-like behavior depending on the experimental context, but never both simultaneously in a single observation. This principle extends beyond physics, carrying philosophical implications about the limits of knowledge and the role of observation in defining reality. In a sense, complementarity tells us that the universe does not present itself as a single, fixed picture, but offers different facets that must be explored through carefully designed experiments. It is both a scientific and a philosophical lens, reminding us that the act of measurement is not passive, but intimately linked to the phenomena we seek to understand. Alternative interpretations expand on this idea and offer different perspectives on the underlying mechanics. Louis de Broglie, in 1924, proposed the pilot wave theory, suggesting that particles are guided by an underlying wave, moving deterministically along trajectories influenced by this guiding field. Decades later, David Bohm developed hidden variable theories, formalizing this idea in a way that preserves determinism while reproducing the predictions of standard quantum mechanics. These approaches emphasize that wave-particle duality need not be a paradox, but can be seen as the interaction between a particle and a guiding, probabilistic wave field. Though not the mainstream interpretation, these models provide valuable insights and have inspired experiments that test the very foundations of quantum theory. A remarkable set of experiments known as delayed choice experiments, first conceptualized by John Archibald Wheeler, further illuminate the interplay between observation and reality. In these experiments, the decision about how to measure a photon, whether to observe it as a particle or as a wave, is made after it has entered the experimental apparatus. Surprisingly, the outcome conforms to the choice made, suggesting that the behavior of light is not fixed until it is measured. These experiments do not violate causality, but highlight the contextual nature of quantum phenomena, where the act of observation plays an essential role in determining the properties we record. Such results reinforce the idea that duality is not merely theoretical, it manifests in ways that can be observed, quantified, and repeated in laboratory settings around the world. Experimental demonstrations of duality abound. In the famous double-slit experiment, light passing through two narrow openings creates interference fringes on a screen, a clear signature of wave behavior. Yet if detectors are placed to observe which slit each photon passes through, the interference disappears, and the photons behave like discrete particles. Modern variations, including single photon sources, confirm that even individual photons display this dual behavior. The patterns emerge statistically over many trials, emphasizing the probabilistic nature of quantum mechanics, where certainty for individual events gives way to predictable distributions across large numbers of particles. This interplay between wave-like statistics and particle-like detections is a cornerstone of the duality concept, bridging classical and quantum descriptions. Complementarity and duality also have practical implications for quantum optics. Lasers, interferometers, and quantum communication devices all rely on the controlled manipulation of light's wave and particle properties. Coherent states, entangled photons, and squeezed light illustrate how the dual nature can be harnessed for technology while remaining faithful to the underlying physics. Understanding that light is neither simply a wave nor simply a particle allows scientists to design experiments and devices that exploit both aspects simultaneously. This perspective is essential for the next stages of exploration, where interference, coherence, and entanglement become central to both fundamental research and applications in quantum information science. At a conceptual level, wave-particle duality encourages us to reconsider what it means to observe and measure. It suggests that nature does not conform to our classical expectations, but instead operates according to principles that challenge intuition, requiring frameworks that integrate probability, interaction, and context. Complementarity and delayed choice experiments remind us that light is not passive. Its behavior is entwined with the choices we make in observing it. By embracing these ideas, we gain not only predictive power over light's behavior, but also a deeper appreciation for the subtle architecture of reality, where duality, probability, and measurement are inseparable elements of a coherent and elegant quantum world. The exploration of duality is as much a journey of the mind as it is of the laboratory. Each experiment, each theoretical insight, reveals patterns that are both astonishingly precise and beautifully intricate. From pilot waves to hidden variables, from interference fringes to single photon detections, we see that light refuses to be confined by classical categories. It invites us to think differently, to accept that apparent contradictions can coexist, and to recognize that observation, context, and interpretation are fundamental to understanding the universe. In this delicate balance between waves and particles, certainty and probability, the behavior of light opens a window into the profound and often surprising principles that govern the natural world. In the realm of quantum optics, light reveals behaviors that go far beyond what classical waves or particles alone can explain. One of the most striking developments in the 20th century was the creation of single photon sources, devices capable of emitting light one quantum at a time. These sources allow scientists to observe the behavior of individual photons, rather than large ensembles, providing a window into the fundamental quantum properties of light. By controlling the emission of single photons with precision, experiments can reveal interference, entanglement, and other phenomena that would otherwise be hidden in the averages of classical measurements. This precise control has become a cornerstone for developing quantum communication technologies, where individual photons carry information across long distances with remarkable fidelity. Squeezed light is another fascinating manifestation of quantum optics. In a squeezed state, the uncertainty in one property of light, such as its amplitude or phase, is reduced below the standard quantum limit, while the uncertainty in the complementary property increases. This may sound paradoxical, but it is a natural consequence of the Heisenberg uncertainty principle, which governs all quantum systems. Squeezed light allows for measurements that surpass classical limits, enabling ultra-sensitive detection of gravitational waves, as demonstrated by the Laser Interferometer Gravitational Wave Observatory, and providing practical benefits for high-precision metrology. The manipulation of such light requires careful control of electromagnetic fields and delicate optical setups, highlighting the sophistication of modern quantum experiments. Entanglement, perhaps the most famous feature of quantum mechanics, demonstrates that two or more photons can exhibit correlations so strong that the measurement of one immediately influences the state of the other, regardless of distance. This phenomenon, which Albert Einstein once described as spooky action at a distance, is not just a theoretical curiosity. Experiments in laboratories across the globe, including those guided by Roy J. Glauber, Marlon Scully, and Kai-Lei Chung, have repeatedly confirmed that entangled photons behave in ways that defy classical expectations. Entanglement underpins quantum communication, quantum cryptography, and even emerging quantum computing architectures, allowing information to be transmitted, secured, and processed in ways that exploit the fundamental properties of light itself. One elegant demonstration of quantum behavior is the Hongou-Mandel interference effect, named after the scientists who first observed it in the 1980s. When two identical photons are directed into a beam splitter simultaneously, they tend to exit together from the same port rather than separately, producing a distinctive dip in coincidence detection. This effect illustrates the wave-particle interplay at the quantum scale. Each photon behaves as an indistinguishable entity, whose probability amplitudes interfere, yet the measurement outcomes reveal discrete particle-like detections. Hongou-Mandel interference exemplifies how quantum mechanics requires a probabilistic framework, where the underlying wave functions determine the likelihood of outcomes, while individual events manifest as localized, countable interactions. Experiments involving squeezed light, entangled photons, and single photon sources are not mere demonstrations. They form the basis of practical technologies in quantum communication. Quantum key distribution, for instance, uses single photons to transmit secure encryption keys that cannot be intercepted without detection, leveraging the fundamental properties of quantum measurement. Laboratories at institutions such as the Institute of Photonic Sciences in Barcelona and Harvard University have built networks demonstrating these principles over kilometers of optical fiber, showing that quantum optical phenomena can be scaled from tabletop experiments to real-world applications. These achievements bridge the abstract beauty of quantum theory with tangible benefits, illustrating the profound utility of understanding light at its most fundamental level. Underlying these experimental advances is the theoretical framework developed by pioneers such as Roy J. Glauber, whose work on the quantum theory of optical coherence provided the mathematical tools to describe light in terms of quantum states, correlation functions, and probabilistic amplitudes. Glauber's insights allow physicists to predict how photons behave in complex systems, whether in lasers, cavities, or entangled pairs. Marlon Scully expanded these ideas into the control of quantum states for practical applications, while Kai-Lai Chung contributed to rigorous mathematical foundations that ensure the consistency of quantum predictions with experimental results. Together, these contributions form a comprehensive understanding of non-classical light, where wave and particle aspects coexist and can be manipulated for both fundamental exploration and innovative technology. Even the subtleties of measurement emphasize the counterintuitive elegance of quantum optics. Detecting a single photon involves converting a quantum event into a macroscopic signal, such as an electron avalanche in a photodetector. Yet the overall patterns, interference effects, and correlations emerge only statistically after many repetitions, revealing the underlying probabilistic structure. This balance between discrete detection events and coherent wave-like interference exemplifies the duality that defines light at the quantum level. Each experiment, whether demonstrating squeezed light or entanglement, reinforces the principle that photons are not merely tiny bullets or continuous waves, but entities whose full behavior is revealed only when both aspects are considered together. By exploring single photon sources, squeezed states, entanglement, and interference phenomena such as Hongyu-Mandel, we gain a profound appreciation for the richness of quantum optics. The work of Glauber, Scully, Chung, and many experimentalists illuminates the intricate dance of probability amplitudes, coherence, and measurement outcomes. Light is both delicate and robust, unpredictable at the level of individual quanta, yet precisely describable in aggregate, a system of remarkable subtlety and power. Understanding these behaviors provides not only insight into the fundamental nature of light, but also the tools to shape the technologies of tomorrow, from secure communications to ultra-precise sensing, all while reminding us that the universe operates according to principles far more intricate and elegant than classical intuition might suggest. Through this lens, we see that quantum optics is not merely an abstract theory, but a living, experimentally accessible exploration of reality. The interplay between wave and particle, probability and measurement, coherence and entanglement defines the behavior of light in ways both subtle and profound. As we continue to refine our experiments, improve our technologies, and expand our understanding, the study of non-classical light becomes both a journey of discovery and a practical foundation for a future shaped by quantum principles. When light passes through narrow openings or encounters obstacles, it does not simply travel in straight lines. Instead, it spreads, bends, and forms intricate patterns, a behavior known as diffraction. Augustin-Jean Fresnel, building on the work of Christian Huygens, made significant contributions to understanding these phenomena in the early 19th century. Fresnel introduced mathematical rigor to the concept of wavefronts, showing that each point along a light wave can act as a source of secondary waves, whose interactions produce observable interference patterns. These patterns, consisting of alternating bright and dark regions, are direct evidence of light's wave-like character, yet they also reveal subtle probabilistic behavior when individual photons are considered. Experiments with multiple slits extend this understanding. A multi-slit setup, where light passes through 3 or more closely spaced openings, generates more complex interference patterns than a simple double slit. The resulting distribution of bright and dark fringes depends on the separation between the slits and the wavelength of light, producing patterns that can be precisely predicted using the principles of wave superposition. Each fringe represents a location where the amplitudes of the secondary waves reinforce or cancel each other, creating regions of constructive and destructive interference. When individual photons are sent through such a setup, they arrive as discrete impacts on a detector, yet the accumulated pattern over thousands or millions of photons reproduces the wave-like interference, illustrating the probabilistic nature of quantum mechanics. The Fabry-Perot interferometer provides another example of how interference can be harnessed for precision measurement. This device consists of two parallel reflective surfaces, forming a cavity through which light bounces multiple times. Certain wavelengths resonate within the cavity, producing sharp transmission peaks that can be used to measure extremely small differences in frequency or to resolve fine spectral lines. The device has become essential in laboratories for spectroscopy, optical communications, and even the stabilization of laser frequencies. Its operation depends entirely on the principles of interference, demonstrating how controlled multipath interactions of light can amplify subtle effects and provide practical insight into both classical and quantum behaviors. Interference and diffraction also manifest in the natural world, often in ways that delight the eye. Thin films, such as soap bubbles or oil slicks on water, produce iridescent patterns as light waves reflect off the top and bottom surfaces, creating alternating bands of color. Similarly, certain biological structures like the microscopic scales of butterfly wings or the feathers of peacocks create structural coloration through layers and lattices that act as natural diffraction gratings. These examples illustrate that wave behavior is not confined to laboratory apparatus, but is embedded in the fabric of nature itself. The vivid colors and shifting patterns we observe are the macroscopic expression of countless interactions between waves and surfaces, a harmonious interplay of light's mathematical and physical properties. Even at the scale of individual photons, interference remains a key concept. In single photon experiments, detectors record discrete arrivals, yet when these events accumulate over time, the same interference patterns emerge as predicted by wave theory. Each photon's probability of detection is determined by the superposition of wave amplitudes along the multiple paths available to it. In this sense, the classical wave description provides a map of probabilities, guiding the behavior of individual particles without contradicting their discrete nature. This probabilistic interpretation is central to modern quantum optics and highlights the elegance of wave-particle duality, where classical predictions and quantum measurements coexist in a coherent framework. The mathematical description of these phenomena is straightforward in principle, though rich in implications. The position of interference maxima in a double-slit experiment, for example, can be expressed as d sine theta equals m times lambda, where d is the slit separation, theta is the angle of the fringe relative to the original beam, m is an integer representing the fringe order, and lambda is the wavelength of light. Extending this formula to multi-slit arrangements or resonant cavities like the Fabry-Perot interferometer allows predictions of extremely detailed patterns with remarkable accuracy. These calculations demonstrate how the harmony between wave mathematics and particle observation provides deep insight into the behavior of light across scales. Ultimately, interference and diffraction are more than just visual curiosities or laboratory demonstrations. They reveal the underlying structure of light's interactions, the rules by which photons and waves combine, and the probabilistic principles that govern quantum phenomena. By observing and understanding these patterns, scientists can probe the coherence, wavelength, and phase relationships of light with extraordinary precision, whether in controlled experiments or in natural systems. From rainbow-hued soap bubbles to precisely tuned interferometers, these phenomena exemplify the seamless connection between theory, experiment, and observable reality, illustrating how the intricate behavior of light can be both mathematically predictable and visually enchanting. Through multi-slit setups, interferometers, and natural diffraction effects, we see that light's wave-like properties are not abstract concepts but tangible, measurable, and profoundly beautiful. When combined with the particle perspective, these experiments reveal a universe in which probability, interference, and observation are intertwined. Light does not simply illuminate objects, it encodes the history of its paths, interacts with its environment, and responds to measurement in ways that reveal the fundamental principles of quantum mechanics. In this delicate dance of waves and particles, the patterns of interference and diffraction become a gateway to understanding both the visible world and the hidden quantum structures that govern it, reminding us that light is at once ordinary, extraordinary, and endlessly fascinating. Light is more than just brightness and color. It carries an orientation, a directionality in its oscillations that we call polarization, In a linearly polarized beam, the electric field oscillates in a single plane, creating a uniform direction of vibration. Circular polarization occurs when the electric field rotates steadily as the wave propagates, tracing a helix along the direction of travel. Elliptical polarization is a more general form, where the tip of the electric field vector traces an ellipse, combining characteristics of both linear and circular polarization. Understanding these forms is essential not only for optics but for technologies that manipulate light for precise control, from imaging systems to communications. Polarization also reveals deeper aspects of light in the quantum realm. Each photon carries a property known as spin angular momentum, which corresponds to the intrinsic rotation of the photon. This spin can take on discrete values corresponding to right-handed or left-handed circular polarization. Beyond this, light can also possess orbital angular momentum, a property of the wavefront's spatial structure, rather than the intrinsic spin of individual photons. Work by Dennis G. Greer and others has shown that photons with orbital angular momentum can form twisted helical wavefronts, often called optical vortices, which can carry information or exert torque on microscopic particles. These discoveries have expanded our ability to manipulate and understand light, revealing properties invisible to casual observation. Applications of polarization and angular momentum are both practical and profound. In optical trapping, tightly focused beams of polarized light can hold and move microscopic particles with incredible precision, enabling experiments in biology, chemistry, and materials science. Quantum information systems exploit the spin and orbital properties of photons to encode and transmit data securely, with polarization states forming the basis of qubits. In advanced microscopy, controlling polarization enhances contrast and reveals structures that would otherwise be hidden, allowing scientists to explore cellular processes at submicrometer scales. Each application relies on a precise understanding of how light's orientation interacts with matter, demonstrating that polarization is not merely a theoretical concept, but a tool with tangible impact. Even in nature, polarization creates striking visual effects. Atmospheric phenomena, such as halos around the sun or moon, arise from the interaction of light with ice crystals in the upper atmosphere, which refract and rotate the polarization of passing light. Similarly, scattering of sunlight in the sky produces partial polarization that can be detected with polarizing filters, revealing patterns invisible to the unaided eye. These examples demonstrate that polarization is not confined to laboratory setups, but is an inherent property of light that influences both natural beauty and practical observation. By considering polarization alongside wavelength, intensity, and coherence, we gain a fuller picture of light's multifaceted behavior. The mathematics of polarization connects classical wave descriptions with quantum concepts. Classically, the orientation of the electric field vector describes the polarization state, which can be represented by vector addition or rotation matrices. Quantum mechanically, the polarization corresponds to the spin state of the photon, which can be described as a superposition of basis states representing horizontal and vertical linear polarization, or right-handed and left-handed circular polarization. These two frameworks are complementary. Classical models provide intuition about wave interactions and propagation, while quantum descriptions explain measurement outcomes, entanglement, and single photon behavior. Together, they form a cohesive understanding of how light carries information and interacts with the world. Practical demonstrations make these abstract ideas more tangible. When linearly polarized light passes through a polarizing filter, the transmitted intensity varies depending on the relative orientation of the light and the filter, following Malus's law. Circularly polarized light can rotate in optical systems to create controlled interference effects, while optical vortices exert torque on small particles suspended in a fluid, causing them to spin or orbit in predictable patterns. These effects provide clear evidence of light's angular momentum and illustrate how polarization can be harnessed for precise manipulation. By exploring polarization, spin, and orbital angular momentum, we see that light is far richer than the simple waves or particles we often imagine. Its orientation, rotation, and structured wavefronts reveal a wealth of information and possibilities, linking classical theory, quantum mechanics, and practical applications. From optical vortices twisting tiny particles to atmospheric halos casting delicate rings around the sun, the subtle properties of polarized light remind us that even familiar illumination contains layers of structure, complexity, and beauty waiting to be observed and understood. Modern experimental techniques allow us to explore light in ways that would have been unimaginable a century ago, revealing both its wave and particle characteristics with remarkable precision. Ultrafast lasers, for instance, generate pulses of light lasting mere femtoseconds, a millionth of a billionth of a second. These incredibly brief bursts allow scientists to observe dynamic processes at atomic and molecular scales, capturing events such as electron motion within atoms or energy transfer in photosynthetic systems. By producing highly controlled, coherent light, ultra-fast lasers provide a laboratory environment in which both interference patterns and single photon interactions can be measured, bridging the classical and quantum descriptions of light. Single photon detectors are another critical advancement. These devices can register the arrival of individual photons with extremely high efficiency and minimal noise, enabling experiments in which one photon at a time is emitted and measured. Such experiments have confirmed wave-particle duality in striking ways, demonstrating that even isolated photons produce interference patterns when their probabilities are considered collectively. The work of experimentalists like Serge Haroche and David Wineland has been instrumental in this field. Haroche's cavity quantum electrodynamics experiments trap photons between reflective mirrors, allowing precise observation of their interactions with atoms, while Wineland has used trapped ions to manipulate individual photons and electrons, revealing quantum behaviors with unprecedented clarity. These achievements demonstrate that the duality of light is not an abstract principle, but a phenomenon that can be directly observed and quantified. Cavity quantum electrodynamics, or cavity QED, is particularly elegant in its simplicity and power. By placing atoms or ions in a resonant optical cavity, the interaction between light and matter is enhanced, making it possible to observe effects such as photon emission, absorption, and entanglement at the level of single quanta. Researchers can control the environment so precisely that they can add or remove photons and measure the resulting changes in the system, offering an intimate view of the quantum dynamics that underlie the familiar phenomena of reflection, refraction, and emission. These experiments also illustrate how classical electromagnetic waves and particle-like photons coexist in a unified framework, with theory and observation reinforcing one another. Weak measurements and quantum tomography provide further insight into light's behavior. In weak measurements, the disturbance to the quantum system is minimized, allowing researchers to extract information about the probability distribution of a particle's position or momentum without collapsing its wave function entirely. Quantum tomography, on the other hand, reconstructs the complete quantum state of light from a series of measurements, revealing the amplitude, phase, and coherence properties of photons in a highly detailed way. These techniques not only validate theoretical predictions, but also allow experimentalists to explore subtle phenomena such as superposition, entanglement, and interference in unprecedented detail. By combining weak measurements with single photon detection and ultra-fast laser pulses, scientists can probe the quantum nature of light across multiple scales and contexts. The precision and sophistication of these experiments require careful alignment, high-quality optics, and stable environmental control. Lasers must maintain consistent frequency and phase, mirrors must be nearly perfect, and detectors must operate with minimal background noise. Despite these technical challenges, the results consistently confirm that light behaves in ways predicted by quantum theory. Interference patterns appear even with individual photons, energy exchanges occur in discrete quanta, and correlations between entangled particles defy classical intuition. The experiments are both delicate and robust, providing a reliable bridge between the abstract mathematics of quantum mechanics and the tangible behavior of light in the laboratory. Through these modern techniques, the wave-particle duality first observed in historical experiments becomes tangible and manipulable. Scientists can now generate, guide, and measure individual photons, create coherent ensembles, and explore their interactions with atoms and materials with exquisite control. By observing light in these ways, we gain a deeper appreciation for the interplay between theory and experiment, between the probabilistic behavior of individual photons and the deterministic patterns predicted by classical wave models. The delicate balance between measurement, coherence, and interaction exemplifies the subtle elegance of quantum optics, where every experiment reveals not only the fundamental properties of light, but also the remarkable ingenuity of those who have learned to observe, manipulate, and understand it with unprecedented precision. These advances have profound implications beyond the laboratory. They underpin technologies such as quantum communication, secure encryption using single photons, high-resolution imaging in microscopy, and even the detection of gravitational waves. Each application relies on a detailed understanding of how light behaves under controlled conditions, validating centuries of theoretical development while pushing the boundaries of what is possible. By mastering the techniques of ultrafast lasers, single photon detection, cavity QED, weak measurement, and quantum tomography, modern physics demonstrates that light is a versatile, deeply structured, and extraordinarily revealing phenomenon, connecting the smallest scales of quantum behavior with the vast expanse of technological and natural applications. The principles of light that we have explored do not remain confined to laboratories or abstract theory. They form the backbone of modern technology, where wave and particle behaviors are harnessed in elegant and practical ways. Photonics, the science of generating, controlling, and detecting light, has become a critical field for innovation. Optical computing, for instance, uses light to perform calculations and transmit information at speeds far exceeding conventional electronics. By exploiting the coherence and interference properties of light, optical circuits can process data with minimal energy loss and extraordinary bandwidth, opening possibilities for faster, more efficient computing systems. Quantum cryptography takes advantage of the discrete particle-like nature of photons to secure information. In quantum key distribution, single photons carry encryption keys, and any attempt at interception alters the state of the photons, revealing the presence of an eavesdropper. This remarkable interplay between measurement and the fundamental duality of light ensures that information can be transmitted with a level of security unattainable through classical methods. The development of these technologies relies not just on abstract principles, but on precise control of photon properties such as polarization, coherence, and timing. Another breakthrough in applied photonics comes from photonic crystals, first explored extensively by Eli Yablonovich in the late 1980s. These materials contain periodic structures that influence the motion of photons, creating band gaps where certain wavelengths cannot propagate, much like how semiconductors control the flow of electrons. Photonic crystals are used to manipulate light in lasers, optical fibers, and sensors, allowing engineers to confine, guide, and filter light with precision. They demonstrate the power of structured materials to interact with light at scales comparable to its wavelength, a direct application of understanding interference, diffraction, and coherence. Beyond computation and communication, light plays a central role in imaging and sensing technologies. LiDAR, or light detection and ranging, uses pulses of light to map environments with millimeter-scale precision. Autonomous vehicles rely on LiDAR to detect obstacles, while atmospheric scientists employ it to study aerosols and cloud formations. Similarly, OLED displays utilize the controlled emission of light from organic materials to produce vivid colors and high contrast ratios, taking advantage of the quantum efficiency of photons to achieve energy-efficient illumination. Solar cell technology also benefits from precise control over light absorption, reflection, and photon management, with engineered surfaces and multi-junction cells maximizing energy capture from the sun's broad spectrum. In all of these applications, the dual nature of light is central. Wave phenomena such as interference and diffraction are exploited to design photonic circuits, improve imaging resolution, and filter specific wavelengths, while particle properties ensure discrete energy delivery and quantum security. The practical deployment of these principles reflects an elegant synthesis of classical and quantum understanding, turning foundational experiments and theories into tangible benefits for society. Whether guiding photons through complex optical circuits, encoding information in single particles, or enhancing the efficiency of solar energy, engineers and scientists translate the abstract behavior of light into tools and technologies that shape the modern world. The beauty of applied photonics lies in the subtlety with which these principles are integrated. Lasers must maintain coherence over meters or kilometers, single photon sources require precise timing, and photonic crystals depend on nanometer-scale structuring. Each technological advance reflects a deep understanding of light's fundamental properties, demonstrating how theory and experiment converge to create functional systems. The practical outcomes are impressive. Faster computing, secure communications, high-resolution imaging, and renewable energy optimization, all made possible by manipulating light with knowledge that traces back to Planck, Einstein, Fresnel, and others. By connecting duality, coherence, and structured materials to real-world applications, we see that light is not merely a tool for illumination, but a medium for innovation. It carries information, exerts forces, and interacts with matter in ways that can be engineered for maximum effect. The technologies of today and the visions of tomorrow rely on a careful balance between wave and particle properties, classical and quantum insights, and experimental precision. In exploring photonics, quantum cryptography, photonic crystals, LiDAR, OLEDs, and solar cells, we observe how light transforms from a subject of curiosity into a versatile and powerful resource, demonstrating the elegance, utility, and enduring fascination of this remarkable phenomenon. When we turn our gaze to the cosmos, light becomes more than illumination. It is a messenger, carrying information across incomprehensible distances and revealing the structure and history of the universe itself. One of the most striking phenomena in this context is gravitational lensing, predicted by Albert Einstein's theory of general relativity in 1914. When light passes near a massive object, such as a galaxy or black hole, the curvature of space-time bends its path, much like a lens distorts the view of objects behind it. Observations of distant quasars and galaxies reveal arcs and multiple images, providing both a spectacular visual effect and a precise tool for measuring the distribution of mass, including the elusive dark matter whose presence is inferred but cannot be directly seen. Vera Rubin's pioneering work in the 1970s dramatically advanced our understanding of dark matter. By measuring the rotation curves of spiral galaxies, she found that stars in the outer regions orbited far faster than could be explained by the visible mass alone. Light from these stars, redshifted by the Doppler effect, provided the data necessary to calculate the gravitational pull of the unseen mass. Rubin's meticulous observations offered compelling evidence that ordinary matter accounts for only a fraction of the universe's total mass, with the remainder hidden yet profoundly influential on the paths of photons travelling through galaxies. The cosmic microwave background, discovered and mapped in detail by George Smoot and his collaborators at the Cosmic Background Explorer, and later the Wilkinson Microwave Anisotropy Probe, offers another extraordinary insight. This faint glow, a remnant of the Big Bang, fills the universe and carries with it tiny temperature variations that encode the distribution of matter in the early cosmos. By analysing the anisotropies in the background, scientists can infer the density fluctuations that would eventually give rise to galaxies and clusters. These observations demonstrate that even the oldest light in the universe retains subtle structure, governed by both classical wave behaviour and quantum interactions that influenced the primordial plasma. Light travelling near extreme gravitational fields also reveals remarkable relativistic effects. Photons skimming the event horizon of a black hole experience extreme bending, time dilation, and energy shifts. These phenomena are visible in images of black hole shadows captured by the Event Horizon Telescope, and in X-ray spectra of accretion disks spiraling into black holes. The precise measurement of redshifts, intensity, and polarization of this radiation provides insight into the dynamics of space-time and the energy distribution of matter under extreme conditions. Observing these effects requires an understanding of both the wave-like propagation of light through curved space-time and the particle-like interactions with high-energy matter near the event horizon. The duality of light becomes a powerful tool for understanding the universe. Wave properties explain interference effects, diffraction by interstellar dust, and polarization induced by cosmic magnetic fields, while particle properties account for energy transfer, photon counts in detectors, and the interaction of light with individual atoms in distant clouds. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories exploit both aspects simultaneously, capturing images, spectra, and temporal variations that reveal phenomena from supernovae to gravitational lensing events. Every photon arriving from the edge of the observable universe carries encoded information, a testament to the remarkable continuity of light across billions of years. Redshift measurements are central to understanding cosmic expansion. As light travels through the expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. Observations of distant galaxies show redshifts that increase with distance, a phenomenon first quantified by Edwin Hubble in the 1920s. These measurements underpin our understanding of the universe's rate of expansion, the distribution of dark energy, and the evolution of cosmic structures over billions of years. When combined with measurements of the cosmic microwave background, gravitational lensing, and galactic rotation curves, redshift data helps construct a cohesive picture of a dynamic and evolving cosmos. Even phenomena closer to home, such as atmospheric halos around the Sun or Moon, provide an instructive analogy to cosmic effects. Ice crystals in the upper atmosphere refract and polarize sunlight, producing concentric rings, arcs, and color variations. While small in scale, these effects demonstrate the principles of diffraction, interference, and polarization that govern light across the universe. In astrophysics, the same principles operate on a vastly larger scale, where light traveling millions of light years is bent, split, and shifted by gravitational fields, interstellar plasma, and cosmic magnetic influences. Observing and interpreting these effects requires a careful balance of wave and particle models, reflecting the duality of light that we have traced from laboratory experiments to quantum optics. Through the study of cosmic light, we gain both quantitative insight and aesthetic wonder. Light from distant stars, galaxies, and cosmic background radiation allows us to map unseen matter, measure velocities, and understand the evolution of the universe. The interplay of wave interference and photon detection, of relativistic redshifts and gravitational lensing, shows that the duality of light is not an abstract curiosity, but a practical tool for exploring reality on the grander scales. Every photon arriving from the cosmos is a messenger, carrying information shaped by the principles of physics, from quantum mechanics to general relativity, and connecting us to the universe in ways both profound and deeply beautiful. By reflecting on these cosmic phenomena, we can appreciate the elegance and subtlety of light as both wave and particle. It allows us to interpret the faint glow of the earliest photons, to track the curvature of space-time around massive objects, and to measure the hidden scaffolding of dark matter that governs the motions of galaxies. The universe, in this sense, is a laboratory of extraordinary scale, where the principles of light reveal the invisible and illuminate the history, structure, and dynamics of all that exists. Observing cosmic light reminds us that the duality we have studied in the laboratory is not limited to Earth, but is a fundamental property woven into the fabric of the universe itself. Beyond the well-established frameworks of classical and quantum optics, physicists have explored alternative theories that challenge our understanding of light and its behavior. Stochastic electrodynamics is one such approach, proposing that the vacuum is filled with random electromagnetic fluctuations that interact with charged particles. In this framework, the apparent quantum behavior of light emerges from interactions with these underlying stochastic fields. While not mainstream, this perspective offers a classical-like explanation for phenomena usually attributed solely to quantum mechanics, such as zero-point energy effects and the Casimir force, suggesting that the boundary between classical and quantum descriptions may be more nuanced than often assumed. Pilot wave extensions, inspired by the ideas of Louis de Broglie and developed further by David Bohm, offer another compelling perspective. In these models, particles are guided by underlying wave fields that determine their trajectories, allowing deterministic motion while reproducing the statistical predictions of quantum mechanics. Photons, in this interpretation, travel along specific paths influenced by the wave function, which acts as a guiding field. This approach challenges the conventional notion that quantum behavior is fundamentally probabilistic, proposing instead that probabilities arise from our lack of knowledge about the complete system. Experiments continue to test these hypotheses, exploring whether hidden variables might exist beneath the surface of observed quantum phenomena. Emergent photon models further expand the conceptual landscape. These theories treat photons not as fundamental entities, but as collective excitations arising from deeper structures in the electromagnetic field. Such models explore whether light, and indeed all quantum particles, could emerge from a more fundamental medium or network of interactions. By considering photons as emergent rather than fundamental, scientists investigate the possibility that the duality of light, the particle-wave behavior, and even entanglement might arise naturally from underlying dynamics, rather than being axiomatic properties of nature. These speculative frameworks push the boundaries of traditional interpretation, prompting creative thinking about the origin and nature of light. John Bell's theorem provides a rigorous test of hidden variable theories, demonstrating that no local hidden variable model can fully reproduce the predictions of quantum mechanics. Experiments based on Bell inequalities have repeatedly confirmed the non-local correlations predicted by quantum theory, showing that entangled particles exhibit correlations stronger than any classical mechanism could explain. This has profound implications for interpretations of light and its duality, ruling out a wide class of deterministic hidden variable models while leaving room for non-local or contextual theories such as pilot wave approaches. The elegance of Bell's work lies in its clarity. It translates philosophical questions about the completeness of quantum mechanics into experimentally testable predictions, bridging theory and observation. Richard Feynman introduced yet another lens through which to view light with his path integral formulation. In this framework, a photon does not follow a single, predetermined path from source to detector. Instead, it traverses all possible paths simultaneously, and each path contributes a probability amplitude to the final outcome. By summing over these amplitudes, the correct interference pattern or detection probability emerges. This approach provides an intuitive picture for understanding quantum phenomena, from simple double-slit experiments to complex interactions in quantum electrodynamics. The path integral formulation highlights the inherent probabilistic nature of light, while maintaining a unifying mathematical structure that accommodates wave-particle duality. These alternative frameworks invite reflection on the richness and subtlety of light's behavior. Stochastic electrodynamics emphasizes the influence of vacuum fluctuations. Pilot wave models introduce deterministic guidance, and emergent photon theories suggest that light itself may arise from deeper underlying structures. All of these approaches, alongside Bell's theorem and Feynman's path integrals, expand our conceptual understanding and offer complementary ways to interpret phenomena that classical or standard quantum models might leave unexplained. They remind us that light is not merely a laboratory curiosity, but a tool for exploring the foundations of reality itself. Exploring these speculative ideas encourages a mindset of curiosity and openness. Each framework, whether confirming, extending, or challenging standard interpretations, provides insight into the principles governing light's duality. Even when models remain unproven or are largely conceptual, they stimulate the design of experiments that probe deeper into the nature of photons, coherence, entanglement, and interference. In this calm, exploratory domain, theory and observation are intertwined, and light serves as a bridge between what we can measure, what we can imagine, and what may ultimately reveal the underlying architecture of the universe. In considering stochastic fields, pilot waves, emergent excitations, and probabilistic path integrals, we recognize that light's behavior is both profoundly familiar and fundamentally mysterious. It manifests as particles, waves, coherent beams, and entangled pairs, all governed by principles that are continually tested, refined, and occasionally challenged. By engaging with these alternative theories, we see that the study of light is not merely about photons or waves, but about exploring the conceptual foundations of reality itself. Each speculative idea, whether widely accepted or on the fringe of physics, invites us to think differently, to question assumptions, and to embrace the elegant complexity that defines the behavior of light in the quantum world. Light is not just a phenomenon observed in laboratories or captured by telescopes. It is woven into the very fabric of the natural world, producing some of the most captivating displays we can witness. Bioluminescence, for example, is the ability of certain organisms to produce light through chemical reactions within their bodies. Fireflies, deep-sea fish, and some species of fungi emit photons with extraordinary efficiency, converting chemical energy into light with minimal heat loss. This natural light arises from molecular interactions at the quantum level, where electrons in specific molecules absorb and release energy in discrete quanta, producing photons with well-defined energies and wavelengths. The glow of a firefly is not just enchanting, it is a tangible manifestation of quantum mechanics in everyday life. Iridescence found in the wings of butterflies, beetles, and certain birds is another striking example of nature exploiting the properties of light. The microscopic structures on these surfaces act as diffraction gratings or multi-layer reflectors, splitting and recombining light waves to produce shimmering colours that shift with viewing angle. The morpho butterfly, native to Central and South America, is a classic example, with wings that appear vivid blue despite containing no pigment for that colour. The effect arises from interference between reflected light waves, creating constructive and destructive patterns. Even though individual photons are detected as discrete events when interacting with the eyes of a predator or a human observer, the collective wave behavior produces the striking iridescent patterns that have fascinated scientists and artists alike. Auroras, the natural light displays in polar regions, provide yet another window into the interplay between photons and quantum phenomena. Charged particles from the solar wind collide with atoms and molecules in Earth's upper atmosphere, exciting electrons to higher energy levels. When these electrons relax back to lower energy states, they emit photons at characteristic wavelengths, producing the shimmering curtains of green, red, and purple light that stretch across the night sky. The precise color and intensity depend on the species of atom or molecule, the altitude of the collision, and the energy of the incoming particles. This is a clear example of light-matter interaction governed by discrete energy transitions, illustrating the particle-like behavior of photons, while the overall shapes and movement of auroral structures are described by wave-like propagation through the magnetic field. Structural coloration in nature extends beyond butterflies and birds, appearing in peacock feathers, opal gemstones, and even the shells of certain beetles. These colors arise from repeated microstructures, thin films, and lattice patterns that diffract and interfere with light. Unlike pigment-based coloration, which absorbs certain wavelengths, structural coloration relies on the coherent superposition of reflected waves to amplify some colors and cancel others. Here again, the wave properties of light are essential, yet the photons themselves deliver discrete energy to the eyes of observers, bridging classical and quantum perspectives seamlessly. These naturally occurring photonic structures have inspired biomimetic designs in engineering, including anti-counterfeiting features, reflective coatings, and photonic devices that mimic the precise control of light seen in nature. Even in these familiar and seemingly ordinary phenomena, the dual nature of light is evident. Each photon carries energy in discrete packets, yet interference and diffraction patterns emerge from the collective wave behavior. The quantum interactions at the molecular or atomic scale produce the vivid visual effects we can observe with our own eyes, connecting the microscopic world to the macroscopic display. The shimmering scales of a butterfly, the glow of a firefly, or the dancing aurora overhead are not merely beautiful. They are demonstrations of fundamental principles that have been studied in physics laboratories around the world, from single photon detectors to advanced optical microscopes. By observing these natural examples, we gain insight into the elegance and subtlety of light as it interacts with matter. Wave-particle duality is not a concept confined to thought experiments or abstract equations. It manifests continuously in the environment around us. Nature has long taken advantage of interference, diffraction, and quantized energy exchanges to create signals, camouflage, and communication. In doing so, it provides an accessible and calming demonstration of quantum mechanics at work, showing that the laws of physics govern not only distant stars and laboratory experiments, but also the living, breathing world we inhabit. Through bioluminescence, iridescence, auroras, and structural coloration, we see that light is both playful and precise. It can be harnessed by organisms for survival, orchestrated by atmospheric and magnetic forces for spectacular displays, and structured at the nanoscale to produce intense color. These everyday quantum marvels remind us that even phenomena we encounter casually are rooted in deep physical principles, where the behavior of individual photons and their collective wave interactions create the beauty, complexity, and wonder that surround us. In observing and contemplating these natural displays, we engage not only with the physics of light, but with the artistry of nature itself, where science and beauty coexist seamlessly. The study of light continues to push the boundaries of what is possible, taking us from classical optics and quantum mechanics into the frontier of emerging technologies and experimental physics. One of the most exciting areas of research is the development of a quantum internet, where entangled photons serve as carriers of information across vast distances. In this paradigm, individual photons are linked in such a way that the state of one immediately influences the state of another, even when separated by kilometers or potentially even satellites in orbit. These entangled networks promise communication that is not only extraordinarily secure, but also capable of performing tasks that classical systems cannot achieve. Institutions such as the Institute of Photonic Sciences, or ECFO in Barcelona, and the pioneering experiments of Anton Zeilinger in Vienna, have demonstrated the feasibility of long-distance quantum teleportation, where the quantum state of a particle can be transferred from one location to another without physically moving the particle itself. Ultra-fast spectroscopy represents another frontier, using laser pulses lasting only femtoseconds to probe the dynamics of atoms, molecules, and chemical reactions in real time. These fleeting bursts allow scientists to track electrons as they shift between energy levels, observe vibrational modes in molecules, and even capture the initial steps of photosynthesis at the quantum level. By exploiting both the wave-like coherence and particle-like discreteness of photons, researchers can extract extraordinarily detailed information about the behavior of matter under extreme precision, revealing processes that unfold on timescales billions of times faster than a blink of an eye. Such techniques have transformative potential for chemistry, materials science, and the development of new quantum devices. Quantum encryption and teleportation protocols are closely linked to these experimental advances. In quantum key distribution, single photons encode encryption keys, and any attempt at interception produces detectable changes in the system, providing a level of security unattainable with classical methods. Teleportation experiments, as performed by Zeilinger and colleagues, exploit entangled photons to transfer the exact quantum state of one particle to another distant particle, effectively recreating its properties without direct transport. While these protocols remain at the cutting edge of research, they demonstrate that the duality of light, its wave-particle nature, is not just a theoretical curiosity, but a practical resource that can be harnessed for computation, secure communication, and advanced sensing. Advanced imaging techniques also benefit from these principles. Quantum-enhanced microscopy uses entangled photons or squeezed light to surpass classical resolution limits, allowing the observation of delicate structures in biological samples without damaging them with high-intensity illumination. By controlling the number, timing, and correlation of photons, researchers can improve signal-to-noise ratios and extract information that would otherwise remain hidden. These applications highlight the extraordinary versatility of light and demonstrate how fundamental understanding of wave-particle duality directly informs technological innovation. Frontier research continues to uncover mysteries that challenge and inspire. Experiments manipulating entangled photon networks over hundreds of kilometers, including satellite-based demonstrations, suggest that quantum correlations may be exploited at scales once thought impossible. The combination of ultrafast pulses, precise control of polarization and coherence, and advanced detection techniques allows researchers to observe phenomena that blur the distinction between classical and quantum regimes. Each experiment, each photon tracked or manipulated, adds another layer of insight into the profound principles governing light and its interaction with matter. The future of quantum light is as much about exploration as it is about application. Theoretical proposals envision networks of entangled nodes spanning continents, teleportation protocols linking quantum processors, and sensors capable of detecting gravitational waves or subtle magnetic fields with unprecedented sensitivity. These possibilities rely on careful manipulation of the duality inherent in light, leveraging its wave-like interference and particle-like discreteness to achieve outcomes that defy classical expectations. Research at ICFO and in laboratories worldwide demonstrates that these concepts are not simply speculative. They are increasingly realizable through precise engineering and innovative experimental design. Even as we advance technologically, light retains its capacity to inspire awe. Each photon traveling through a quantum network, each pulse dissecting a chemical reaction in femtoseconds, each entangled pair linking distant locations, reminds us that nature is governed by principles both subtle and profound. The duality of light, first glimpsed in laboratory experiments over a century ago, now serves as a tool for exploring the universe at the smallest scales, for transmitting information in fundamentally secure ways, and for uncovering the deepest structures of matter and energy. By contemplating these emerging applications, we recognize that the study of light is an ongoing journey, one where mystery and discovery coexist. Quantum optics, entangled networks, ultra-fast spectroscopy, and advanced imaging illustrate the breadth of possibilities that arise when we embrace the full complexity of photons, waves, and quanta. The insights gained from these studies will shape the technologies of tomorrow, while continuing to challenge our intuition, spark curiosity, and remind us that light is simultaneously ordinary and extraordinary, tangible and enigmatic, a medium through which we explore the boundaries of reality itself. Light is more than a source of illumination. It is a window into the very nature of reality. Throughout centuries of exploration, from Newton's corpuscles to Planck's quanta, from Fresnel's wavefronts to Zeilinger's entangled photons, we have come to understand that light embodies a profound duality. It behaves both as a wave, spreading, interfering and diffracting, and as a particle, delivering discrete packets of energy, interacting with matter in quantized ways. This duality is not a paradox to be resolved, but a principle to be embraced, a reminder that nature is subtler and more intricate than our everyday perceptions suggest. The mysteries of light continue to unfold. Even after decades of quantum optics, ultra-fast spectroscopy, and cosmic observations, new phenomena emerge that challenge our intuition. Experiments with single photons, entangled networks, and cavity quantum electrodynamics reveal behaviors that are both astonishingly precise and deeply probabilistic, showing that light is governed by rules that blend determinism with chance. From the iridescence of butterfly wings to the faint glow of the cosmic microwave background, light manifests principles that connect microscopic quantum events with the grand architecture of the universe. Every experiment, every observation, is a reminder that the study of light is ongoing, that each photon carries the potential for discovery. It is also important to recognize the subtle, lesser-known contributions that have shaped our understanding. Scientists such as George Stokes, Jean-Baptiste Biot, Philippe Lenard, and Dennis G. Greer provided insights that often go unnoticed outside specialized fields, yet their careful measurements and theoretical innovations were essential to building the frameworks we rely on today. Their work demonstrates that progress in science is a cumulative and collaborative effort, blending meticulous observation with creative theorizing, and that even small contributions can illuminate the path toward profound understanding. Light also bridges science and beauty. Natural displays such as auroras, bioluminescence, structural coloration, and polarized sky patterns remind us that the physical principles we study have aesthetic resonance. The interference fringes in a laboratory experiment echo the iridescent colors on a butterfly's wing, and the polarization of sunlight through ice crystals mirrors subtle laboratory measurements of photon spin. These connections reveal that scientific inquiry and sensory experience are intertwined, that understanding the mechanisms of light enhances our appreciation of the world's elegance, and that observation, calculation, and reflection are all part of a shared journey toward comprehension. Philosophically, light teaches us about observation context and the limits of knowledge. Niels Bohr's principle of complementarity reminds us that the properties of light we measure depend on how we choose to measure them, and Wheeler's delayed choice experiments show that even the past behavior of a photon can appear contingent on present observation. Such insights invite a meditative perspective. Reality is not always a fixed, fully knowable landscape, but a dynamic interplay between phenomena and perception, between potentiality and measurement. As we reflect on these ideas, we can appreciate light as both a practical tool and a source of contemplation. Its waves and particles, its colors and polarizations, its quantum uncertainties and cosmic journeys all provide windows into the laws that govern our universe. Light links the microscopic with the cosmic, the experimental with the philosophical, and the beautiful with the deeply instructive. By observing, measuring, and contemplating light, we engage with nature at its most fundamental level, while also nurturing curiosity, wonder, and a sense of calm appreciation. In this quiet reflection, we can let go of the expectation of final answers and instead embrace the elegance and subtlety of light itself. Each photon, each interference pattern, each quantum transition is a reminder that the universe is at once orderly and mysterious, that exploration is never complete, and that the act of observing is itself part of the unfolding story. Light, in all its forms and behaviors, invites us to remain curious, to appreciate subtlety, and to recognize that reality, like the gentle glow of a distant star, can be both comprehensible and endlessly inspiring.